Okay, continuing from last time, we are going to do this example here. Find the points of inflection and discuss concavity. So we have just a polynomial here. In order for us to find the points of inflection, we're going to have to find the second derivative. It's just a polynomial, so this should be easy to do. But let's first take a look at the graph and see if we can see where the inflection point might be. Okay, so just from the graph, we can see where the graph is increasing and decreasing. It's increasing for a while, and then it's decreasing, and then it's increasing again. So we can see a relative maximum and then a relative minimum. So we can see critical numbers. We can see that we should have concave down in this region here. Okay, so we're concave down here, and then we appear to be concave up here. Okay. So now that means that we must switch between concave down and concave up somewhere along the way while we're decreasing. Okay, so somewhere in this region here, we must have an inflection point. So find the points of inflection. That's going to occur somewhere. Looks like between maybe 0 and 1, somewhere in there. And then discuss concavity. We're going to be concave down from negative infinity to wherever that inflection point is for the x coordinate between 0 and 1, it looks like. And then from that point of inflection to positive infinity will be concave up, okay? Just by the graph, right? So the key is that we're going to need to find that point of inflection. And then we're going to have to use this process here, right here, to decide how we are concave, okay? So that's the idea. Now we're going to have to go ahead and do it. So first move is to find the second derivative. So to do that, we need to find the first derivative. So f prime of x equals, so that'll be 6x squared minus 6x minus 12. I'm not going to do anything with that. We're just going to take the second derivative. F prime of x, f double prime of x equals 12x minus 6. Okay, so that's our second derivative. Now we're going to set that equal to 0 so we can find our point of inflection. So then solve for x. I'm going to add 6 to both sides. 12x equals 6 and divide by 12, so x equals 1/2. So just by looking at the graph, we knew it was going to be between 0 and 1, and it is. It's x equals 1/2. Okay, now it says point of inflection here. Okay, it doesn't say x coordinate. This isn't like critical number where we just want the x coordinate. We want the actual point of inflection. So we need the ordered pair. To do that, we need to take the 1/2 and we need to plug it into the original function. So that means we need f of 1/2. Okay, we need the ordered pair. So 1/2 to the third power is 1/8. 1/8 times 2 is 1/4. So we got 1/4 there. Then minus 1/2 squared is 1/4 times 3 is 3/4. So we have 1/4 minus 3/4. And then 12 times 1/2 is negative 6, and then plus 5. Okay? So we have 1/4 minus 3/4. That would be negative 2/4. So we're at negative 1/2. Negative 1/2 minus 6 takes us to negative 6 and 1/2. And then plus 5. Negative 6 and 1/2 plus 5 are probably negative 3/2, right? So the inflection point is 1/2 negative 3/2. And if we look at the graph over here, 1/2 negative 3/2. So this location right here seems like it would be, look at the scale for the y-axis. It does seem like it could be 1/2 comma negative 3/2, okay? So that's probably pretty good. Now, discuss concavity. So the way that we figure out concavity is we're going to set up intervals. So the intervals that we're going to go with are, since we have a point of inflection of 1/2, we're going to go from negative infinity to 1/2, and then 1/2 to positive infinity. All right, since that was our only point of inflection. the x coordinate. So then we have x value for our test number in this interval. A good test number would probably be 0, and then a good test number in the second interval would probably be 1. And we're checking f double prime. All right, now I'm plugging this into the second derivative, and all I care about is the sign. So I plug 0 into the second derivative. I have basically 0 minus 6, so I wind up negative. Negative tells me concave down. Okay? I plug in 1. I wind up with 12. 12 minus 6 is 6, but the point is that it's positive, and that tells me I'm concave up. Okay? But we knew that from the graph already, but we need to know how to do that without a graph. So I'm concave down in the first interval, I'm concave up in the second interval. So now my answer, discuss concavity, is going to be concave down. Okay, now I'm going to say on what intervals? In this case, it's only one interval. Negative infinity to 1/2, and then concave up on what intervals? In this case, again, only one interval, 1/2 to infinity. Okay, and these are open intervals, not closed intervals, because first of all, we can't close on infinity. It has to be open. And second, at 1/2, we are neither concave up nor concave down because we're at an inflection point, so it has to be open there. All right, so these are open intervals. All right, so we have two answers here, the inflection point and discussing concavity. There you go. That's how you do these problems. So let's check out the next one. So find the points of inflection and discuss concavity. Okay. So again, if we look at the graph, we see, actually maybe we don't see. Let's see what we see. What does it look like we have? So starting off as we read the graph from left to right, we should see sort of a dish or a bowl shape here. The bowl would be pointed upward, so we're concave up here. And then a little bit later, our bowl shape would be pointing our bowl downward, so we're concave down. And then a little bit later, we have a bowl shape pointed upward, so we're concave up again. So it seems like we have probably two inflection points. Somewhere in this region, we have an inflection point because we're switching from up to down. And then somewhere in this region, we must have another one because we're switching from down to up. And then it seems like we're just up the rest of the way. So that's what we're kind of looking for, okay? We find the points of inflection. That means we need ordered pairs. And then discuss concavity. We're going to state the intervals on which we're concave up and concave down, okay? So let's get going. We're going to need, to talk about concavity, we need the second derivative. Again, it's a polynomial, so this is very easy to take the derivatives of. We just need f double prime. To get there, we need f prime. So f prime of x is 4x to the third minus 12x squared. So now straight to f double prime of x equals 12x squared minus 24x. That's our second derivative, and we could factor that to make life a little bit easier later on, but I'm just going to leave that alone. Well, actually, you know what? I just got ahead of myself. So we need to set this equal to 0 to solve for x, and now we are going to factor this. So you pull out a GCF, 12x, and then what's left over is x minus 2 equals 0. Factored form is almost always going to be our preferred form anyway, so this is helpful. Okay, now we do zero-part property. So we have 12x equals 0 and x minus 2 equals 0. So x equals 0 on this guy and x equals 2 on this guy. So those are our critical number locations for the x coordinates. But we need points, remember, so we need to come up with the ordered pairs. So we need the y coordinates for both of these. So if I plug in 0, f at 0, the original function, would give me 0, so I have an inflection point at 0, 0. its inflection point. We have 0, 0. And if I plug in 2 into the original, so f at 2 would be 2 to the 4th minus 4 times 2 to the 3rd. So 2 to the 4th, 2, 4, 8, 16, minus 4 times 2 to the 3rd, which is 2, 4, 8. So that would be 16 minus 32. 16 minus 32 is negative 16. So we have another one at the ordered pair 2, negative 16. And if we look, the circles that I drew on this graph, 0, 0 makes sense. We have an inflection point right there. And then 2, negative 16 would be right there. And it sure does look like it could be negative 16 down there, okay? So both of those inflection points make sense based on what we're seeing in the graph, okay? So found the inflection points and then discuss concavity. So the way that we do this algebraically, even though we kind of already know what's going on here, we need to know how to do it algebraically. We set up our intervals. The intervals come from the inflection points. So the negative infinity is where we start. And we're going to the first inflection point, which was 0. And then from 0 to the next inflection point, 2. And then 2 to the next inflection point if we have them. And we keep going, but we don't have any more, so we're just going to go to infinity now. Okay? And then we set up our table. Okay, we're going to go with x values to test. And we're plugging these into the second derivative. So we're giving myself a little bit more room there. All right, so a good number to check in this first interval would probably be negative 1. In the second interval would probably be 1. And then in the third interval, I don't see any real reason to go with anything other than 3, okay? Sometimes you want to really look at the numbers that you're picking. Sometimes these numbers don't really make sense based on the problem. But here, there's no issue, so these are good. Okay, so we take negative 1, we're plugging it into the second derivative, all right? Now we could go back up here, but factored form right here is going to be really nice to work with, okay? So we're going to use the factored form. Remember, all we care about is the sign. So outside, we're going to wind up with a negative number. 12 times a negative 1 is negative 12. I don't care about the number itself, I care about the sign, okay? So we're negative outside. And then negative 1 minus 2. We're going to wind up negative inside as well. So a negative times a negative. Again, I don't care about the number, I care about the sign. It's negative times negative, which is positive. That gives me concave up. Okay, now the second interval. Outside, 12 times a positive gives me a positive. Inside, I have 1 minus 2. That's going to give me negative. So I have outside positive, inside negative. Positive times negative is negative, so I am concave down. And then we have this positive 3 here. 12 times a positive number, outside is still positive. But now inside I have 3, which is bigger than 2, so 3 minus 2 is going to wind up positive. So outside is positive, inside is positive, positive times positive is positive, I am concave up. So that's how that's done, okay? A lot of times we don't care at all about the number, we just care about the sign. That's always the case. Okay, so now we know. So we can set up our discussion of concavity. So I'm starting off concave up here, so I'm going to say concave up. Okay. And that interval is negative infinity to 0. And then my next interval is concave down. So I'm going to say concave down. Okay. And that was from 0 to 2. Okay, now my next interval wound up concave up. So up here, I'm going to go back up to the concave up line, and I'm going to union 2 to infinity. I'm done. Inflection points up here. Put rocks around those so I can spot them easily. Notice the union symbol, big capital U. That's the best way to do it. Okay, so next problem. So this one, find the inflection points and discuss concavity again. Same instructions. We do not have a polynomial this time, so it's going to be a little more tricky. We still need the first derivative to get to the second derivative, so a little bit tougher this time. How am I going to take this derivative is the question. You've got a couple options here. You could think quotient rule. What I want to do is rewrite it. This just comes with experience. If you rewrite this as 6 times x squared plus 3 to the negative first, now you can do a general power rule on this guy. So we have f prime of x equals general power rule. The negative 1 comes down, so now it's negative 6, times what's inside stays the same, plus 3. Decrease the exponent by 1, so it's the negative second, times the derivative of what's inside. That's 2x. Okay, derivative's done. So now we're going to simplify that. Okay, so I'm going to go equals right here. Now the 2x times the negative 6 would become negative 12x. And I see that negative exponent right there, so I'm going to move that to the bottom. So what I have is negative 12x on top, and on the bottom I have the x squared plus 3 squared. That's my first derivative. Okay, now the second derivative, think about it. Probably quotient rule here would be the best move. And then along the way, when I'm taking the derivative of the denominator, I'm probably going to need the chain rule, okay? Or the general power rule, depending on how you want to look at it. So f double prime of x. I have a plan, quotient rule, chain rule, okay? So f prime g minus g prime f over g squared, right? I've been doing this forever, and I still say those things to myself before I do it to get them fresh in my mind, all right? So I have f prime, that gives me negative 12. G, x squared plus 3 squared. All right, now minus g prime f. So minus g prime f. Now g prime is going to be a little bit complicated, and f is just this negative 12x. So what I'm going to do is I'm going to write down the f first, because it was easy. Now I'm going to take care of the g prime. And to do that, I'm going to use the general power rule. So the 2 comes down. Notice the parentheses. Okay, I'm just taking care of things and not confusing myself. So the 2 came down. Now what's inside stays the same. I decrease the exponent by 1, so now it's a 1, so I don't got to bother writing it. And then take the derivative of what's inside. Okay, so all of that is done. Now, divided by the denominator squared. So that's going to be x squared plus 3 squared squared. Squared squared is to the 4th. Okay, the derivative is done. Now it's just a matter of simplifying, and I do want to simplify the numerator because that's going to make my life a little bit easier in a little bit. So I'm going to go equals right here. I'm going to leave the denominator alone for a little bit. So x squared plus 3 to the 4th power. It's going to stick around. Okay, now I want to distribute out in this second term right here. So I have, let's see, 2 times 2x would be 4x. And then we have 4x times negative 12x would be negative 48x squared. But then that minus sign right there would make it positive. So now I have plus 48x squared. So, okay, I have this negative 12 times x squared plus 3 squared, and then plus 48x squared times x squared plus 3. Okay, hopefully I didn't just do too much all at once there. Now, the denominator is x squared plus 3 to the 4th. And if you notice in the numerator, I have an x squared plus 3 in both of those terms. So what I can do is I can divide out an x squared plus 3 from each one of these terms. and x squared plus 3 from this term gets rid of that squared. It gets rid of this entire x squared plus 3, and it gets rid of this fourth and makes it a third power. Okay, so that makes things a little bit simpler. So what I can do now is I can distribute this negative 12 in, because it's no longer squared, it's to the first power. I can distribute the negative 12 in, and that gives me negative 12 x squared minus 36 plus 48 x squared, because there is no x squared plus 3 anymore over there. And then I can combine like terms. So now, and hopefully, really hopefully I'm not doing too much here all at once, I have f double prime of x equals, up top, 48x squared and negative 12x squared would be 36 36x squared minus 36. So there's a GCF there that I can pull out as well. And then over x squared plus 3 to the third power. Okay? And I am going to go ahead and pull out that 36. So 36 comes out, and I'm left with x squared minus 1 over x squared plus 3, that's a 3, to the third power. Okay, so that's my second derivative right there. Now, the reason I pulled that 36 out is because that's a 36. It's going to be 36 no matter what. It's positive. Okay, remember, when I'm dealing with concavity, I care about plus and minus. That's it. I don't care about the number. If I'm sitting here dealing with multiplying by 36, like would be on the left, then I'm dealing with huge numbers, and I'm probably going to have to deal with a calculator, and I don't want to do that. But if I have to deal with x squared minus 1, that's really easy to work with. X squared plus 3, pretty easy to work with. I'm not going to worry about it, okay? So that's why I pulled that 36 out of there. Okay, so that's my derivative here, okay? Second derivative. I'll put a box around it because I got a lot of work on this screen, and I don't want to lose it. Okay, so now I have my second derivative. Now I need to find points of inflection. So what I can do is I can set this equal to 0. I haven't even really looked at the graph. I don't really care. I don't need the graph. I don't want it. I don't have to have it. Okay. We'll look at the graph here in a little while. So I can set this equal to 0 and solve for x. When I do that, I can multiply both sides by the denominator. When I do that, the denominator disappears. Okay. So normally, like beyond this, I probably won't even write this step down, but I'll write it down now. The denominator is now gone. And now I have 36 times x squared minus 1 equals 0. So my next move would be divide both sides by 36. And that leaves me with x squared minus 1 equals 0. So my next move would be add 1 to both sides, and now I have x squared equals 1. And now I would square root both sides, and I have x equals not 1, but plus or minus 1. Okay? So those are the x coordinates for my inflection points. And if I come up here to my graph, I'm going to go with this color here. If I come up here in my graph, positive 1 and negative 1 are where I change concavity. I see on my graph that I seem to be concave up here, and then I switch to concave down, and then I switch to concave up, and plus and minus 1 apparently are the x coordinates when that occurs. Okay, so without even looking at my graph, I came up with numbers that seem to make sense. That's why I didn't look at my graph. So now I need the y coordinates. Okay, so I need to take these plus and minus 1 and go back up to the original function. That's easy enough to do. So original function f at 1 equals 6 divided by 1 squared, which is just 1 plus 3. So I'm going to get 6 over 4, which is 3 halves. And guess what? Because the 1 is being squared, or the negative 1 is being squared, f at negative 1 is going to give me the same thing, 3 halves. Okay? So my inflection points are going to be x coordinates of plus or minus 1 3/2. I got both of them sitting right there. Okay. Plus or minus 1, 3/2. Okay, so now it's just a matter of coming up with my concavity. So the way that I do that is I set up my table, set up my intervals. So I have my first interval will be from negative infinity to my first inflection number, which comes up as -1, and then from -1 to 1, and then from 1 to infinity. And we're going to pick an x value in each one of those intervals, and we're going to go into f double prime to check it. So a good number in negative infinity to -1 might be -2. And then from -1 to 1, 0. And then 1 to infinity, how about 2? Okay, so now we're going to go into f double prime with these test numbers, and we're going to use the factored form. Okay, but before we do anything, I want to look at the factored form of f double prime. First of all, we have the 36 sitting out front. That is always positive, so I can ignore it. Okay, look at the denominator. We have x squared. Whenever I square a number, it winds up positive. Then I have plus 3. So I'm going to have a positive number plus something. That's always going to be positive. And then I'm going to cube it. So no matter what, this denominator is going to be positive. Okay, so I have a positive 36 out front in the numerator. The denominator is always positive. So now the question is just going to be, is the inside of the numerator up here positive or negative? That's the only question. Whatever that winds up being is what my concavity is going to be. So take a look at -2. I go into the numerator in the parentheses. -2 squared is 4. 4 minus 1 is positive 3. So I'm going to wind up positive. We are concave up. I plug in 0. 0 squared is 0 minus 1 is negative. That means I'm going to wind up negative. So I'm concave down. I plug in 2. 2 squared is 4. 4 minus 1, we're positive. We're concave up. Okay? And that's the power of factored form. And that's why all year long we've been saying leave your answers in factored form, okay? Or factor it and then write your answer like that, because we work really well with factors. We don't work well when things are multiplied out. And so that's why we've been trying so hard to get our answers written like this, okay? So formalize your answer. Discuss the concavity. Well, my first interval says I'm concave up, so I'm going to write concave up. And that is going to be from negative infinity to -1. Then my next interval says I'm concave down, so concave down. And that is from -1 to 1. And then my next interval, I'm concave up again, so I'm going to union, and that is from 1 to infinity. And we're done. Okay. Let's go on to the next one. Find the points of inflection and discuss concavity. Sounds familiar. So we have this graph. Now, one of the things that you need to do before you do anything is look for division by 0. If we go back to the previous function, we did have a rational situation, but there was no division by 0 because it was x squared plus 3. There was no chance for division by 0. The denominator was always positive. Okay? But on this one, x squared minus 4 in the denominator, we do have the possibility for division by 0. Okay? So because of that, the first thing we want to do is say we have vertical asymptotes at x equals plus or minus 2. Okay? You can see them right here on the graph. Positive 2 and -2, we have vertical asymptotes. So that causes critical numbers, and it causes concavity, potentially. Okay? So we have to include those in our intervals when we are setting up our table. So we need those immediately. Okay? They're automatic interval makers. So now once we have that, we can go ahead and take our derivatives and get our second derivative set up. Okay, so f prime of x equals, clearly I'm going to need the quotient rule here. I'm just going to go ahead and give you the derivative. It is negative 10x, just to save time, negative 10x over x squared minus 4 squared. And then also to give you time saver here, f double prime of x equals, okay, the numerator is going to be 10 times 3x squared plus 4 divided by, and if you've recognized the pattern that's going on in these, you should know that the denominator is going to be x squared minus 4 to the third. Okay, so now we know that we need to set this thing equal to 0. We know that we're going to multiply both sides by the denominator, and the denominator will be gone. We know that we're then going to divide both sides by 10, and that 10 will be gone. And that's going to leave us with 3x squared plus 4 equals 0. And we know that we're going to solve for x. So that means we're going to subtract 4 from both sides, and we're going to divide both sides by 3. And that's going to give us x squared equals negative 4 thirds. Now when I square root both sides, I'll have x equals plus or minus the square root of negative 4 thirds. But if you're paying attention, you're taking the square root of a negative number. What does that mean? It means that you have an imaginary result. So you can say at this point, therefore, the 3 dots like that is therefore, no additional inflection. Okay? We have inflection in the vertical asymptotes. We have no additional inflection through our work here in the second derivative. Okay? So keep that in mind. We can now set up our table. Intervals, negative infinity to our first vertical asymptote, negative 2, and then from negative 2 to positive 2, and then from positive 2 to infinity. There's a lot of 2's going on there. All right, now, x, and we're going to f double prime with this one. Numbers in our interval, from negative infinity to negative 2, we might try negative 3. And then from negative 2 to 2, we'll probably try 0. And then from 2 to infinity, there's no reason to not use 3. Okay, in your second derivative, I gave you factored form, so we're looking good. Now take a look at it. In the numerator, the 10 outside is always positive. 3x squared, that term will always be positive, and then plus 4, always positive. So the numerator itself is always positive. It's important to see that. Now in the denominator, we're going to have x squared minus 4. That is not necessarily always positive. And then we're going to cube it, also not necessarily always positive. So if the result inside is negative, then when we cube it, we will still be negative. Okay? So it's going to depend on what is inside. If inside is negative, then the result here overall is going to be negative. All right? So keep that in mind. Okay, if I take negative 3 and I plug it in, we know the numerator is going to be positive. Negative 3 squared is 9. 9 minus 4 is 5, which is positive, which means the whole thing is positive. So we're going to be concave up. And we have 0. 0 squared is, of course, 0 minus 4 is negative. We cube that, we're going to be negative, so we're concave down. And 3 squared is 9. So we're back to where we were with the other one. We're going to be concave up. Okay? And if we look at the graph, we see concave up here. We see concave down here. We see concave up here. So what we got here makes sense. So set up our discussion. We started off concave up, so I'm going to write concave up. Okay, concave up, and where were we? From negative infinity to negative 2. So the next we had concave down. and we were -2 to 2, and then we're back to up, so we're going to union and get 2 to infinity going. Okay, that's it. So no additional inflection, but we did have these vertical asymptotes sitting right here. Okay, so we might state that we had vertical asymptotes, but we had no inflection points. That's important. Okay, continuing. Now we have the second derivative test. So we have the first derivative test, now the second derivative test. Okay, it's not that it's the second test of derivatives because we had the first one and now we're on the second one. This is a test that is using the second derivative to do exactly the same thing that the first derivative test was doing. Okay, the first derivative test was using the first derivative to decide whether you had a maximum or a minimum. The second derivative test is using the second derivative to decide whether you have a maximum or a minimum. Okay, so keep that in mind. You have critical numbers first. You find your critical numbers by setting the first derivative equal to 0, just like before with the first derivative test. Okay, but now this time the difference is you're going to find the second derivative, and then you'll plug your critical numbers into the second derivative. Okay, now here's what's happening. You know that critical numbers occur when the function has a horizontal tangent. Okay, we're going horizontal here, so the function has a horizontal tangent, which means that the slope is 0. So that's going to give us a critical number. Okay, now if I take that critical number and I plug it into the second derivative, test numbers in the second derivative will tell me if I'm concave up or concave down. Okay, so that critical number is acting like a test number. So if I plug that test number into the second derivative and I get a positive result, when I plug it into the second derivative tells me that I'm concave up. A positive result tells me I'm concave up, which tells me that the graph is doing this. That means that I must have a relative minimum at that critical number that I plugged in. Okay? Because the critical number was horizontal. The graph was horizontal there at that critical number. So I must have a relative minimum there. Okay? So if I take a critical number and I plug it into the second derivative, this is acting as a test number. That test number tells me that the second derivative is negative. That means that the function has a concavity that's down. But because I plugged a critical number in, I know that the slope at that location is 0 in a concave down situation. That means I must have a relative maximum. Okay? So, yes, this is correct. Why? I just explained it. It's because you are using the second derivative and plugging in a test number, but that test number is where the function itself has a slope of 0. Okay? And because you're plugging in the slope of 0 and getting a value that is telling you what the concavity is, you're paying attention to the concavity, and that is telling you the shape of the graph at that location. Therefore, you are getting a minimum or a maximum. Okay? So find the relative extrema. This is different now than what we've been doing. Find the relative extrema of this polynomial. Okay? Now I'm giving you the graph here, so we kind of already know what's going on. All right? But we can do the second derivative test on this guy. Okay, so let's do that. We need the first derivative first. So f prime of x equals -15 x to the fourth plus 15 x squared. Now we're going to need to find critical numbers off of that. We can do that in a second. I'll get f double prime. So we have now -60 x to the third plus 30 x. Now, since we're doing the second derivative test, we do not need to get inflection. We just need critical numbers, and then we're going to plug those critical numbers into the second derivative. Okay, so critical numbers here. I should probably factor, set it equal to 0 and factor. So we have, pull out a GCF, that would be negative 15x squared. What's left over? X squared minus 1 equals 0. Okay, set it equal to 0, pull out the GCF. Now, this out front is going to be equal to 0, so that means x equals 0. This inside is equal to 0, so that means x squared equals 1, so x equals plus or minus 1. Okay, so my critical numbers are 0 and plus or minus 1. So now what I need to do is I need to take those critical numbers and plug them into the second derivative and see what the second derivative sign is. Okay, the sign is all I care about. I don't care about the number, I care about the sign, because that will tell me concavity. And once I know concavity, I will know if I have a minimum or a maximum. So when x equals 0, f double prime is, okay, if I plug in 0, I get 0. Therefore, what? We'll come back to that. When x equals 1, f double prime is what? So we have negative 60 plus 30. F double prime is negative. Therefore, it's concave down. What does that mean? Relative max. Okay? And when x equals negative 1, f double prime is what? Well, negative 1 cubed is negative 1 times 60 is positive 60 now. And then negative 1 times 30 is negative 30. So we have 60 plus negative 30, which is positive. So we get positive. Therefore, where are we? Concave up. So that is a concave up situation. That is a relative minimum. Okay. Now, it says the second derivative test doesn't work when f double prime equals 0. And that's what we got. When x was 0, f double prime was 0. The second derivative test doesn't work because what happens is we have this situation. The slope is 0 and the concavity doesn't exist there. Okay? What we have is something called the saddle point. We're switching, we have inflection going on at the same time that we have a slope of 0. So there is neither concave up nor down. Okay, it's just neither. So that's it. Okay, that's what you do. Now, technically, we should be finding ordered pairs here because it says find the relative extrema. So we have a relative max at 1. We take that 1 and plug it in. So we have negative 3 there and 5 there, so it's 2. So we have a relative max, and that ordered pair is 1, 2. And then we have relative min at negative 1, and then we got to figure out what that is. So that's going to be negative 1 there, so that's 3. And we have negative 5 there, so minus 5, so negative 2. Okay? And if we look at the graph, relative min, negative 1, negative 2, relative max, 1, 2. So we did it right. Okay? There you go. All right. Find the relative extrema using the second derivative test. So this time we have no graph to look at. We have to rely on our calculus and algebra. So what do we do? we need to probably take a derivative here. You could use a product rule, or nothing says you can't. So what I would do is I would distribute that x cubed in and have x to the fourth minus 4x to the third, and then easily take a derivative. So I have f prime of x equals 4x to the third minus 12x squared. And from there, I can find my critical numbers, set this equal to 0, and solve for x. So now I'm pulling out a GCF of 4x squared, and I'm left with x minus 3. So I'm going to get x equals 0 off of this first one, and x equals 3 off the second one. I need my second derivative, so f double prime of x off of the polynomial off the top. I'm going to get 12x squared minus 24x. I do not need to do anything additional to that. I could factor out a GCF to make it maybe a little bit easier to work with if I wanted to, but I don't need to. So if I plug in the 0, f double prime at 0, I get 0. So I can say at or when x equals 0, neither. Okay, the second derivative test failed. I got 0 for a result, so I get neither on that one. And then when x equals 3, let's see what happens. We get 9 times 12 is 108. And then 24 times 3 is 72. 108 minus 72 is positive. So positive tells me concave up. Concave up tells me relative minimum. Okay? So I have a relative minimum at 3, comma 1. So I plug in 3, and I have 27 minus, or 27 times, so I'm doing f of 3. 3 cubed is 27 times 3 minus 4. So that'd be negative 1. 3, negative 27. There's my relative minimum. That's it. And that is the section, so we're done.